Hello, my name is Bernardo, and in this session, I'll be presenting our work on interleaved sequence RNNs for fraud detection. In this work, our main contributions are: we identify a new type of problem, a sequence composed of many interleaved, irregular, and unbounded subsequences. We propose an efficient batch training technique. We propose an efficient streaming inference technique, and we evaluate our system in two real-life use cases, showing that RNNs outperform the state-of-the-art, saving millions in fraud detection and resources. So, onto our problem. Transactional fraud accounts for billions of dollars lost per year, affecting businesses, banks, and cardholders. In machine learning terms, this means that we are dealing with a binary classification problem, fraud or not fraud, which is extremely class imbalanced, and our sequences are interleaved with each other. In other words, at any given point in time, we can receive transactions from multiple cards, having no control over which arrive when. Finally, our models work in the critical path of approval of these transactions, meaning that in production, they need to predict in a streaming fashion at high throughput rates and with latencies of milliseconds. So, how do fraud systems usually work? Well, the majority of current fraud detection systems employ tree-based classification algorithms, such as random forests, XGBoost, and LightGBM. These systems need to augment data with so-called profiles, which are arithmetic aggregations over the data, to capture the history of a card and its normal usage patterns. These profiles are then sent as features to the models. However, these same profiles are often a bottleneck. During the iterative process of model development, computing these features is a tedious task involving high costs in terms of time and computational resources. For online prediction, these profiles must be either computed in memory or fetched externally, in real time, posing a complex engineering problem given the strict latencies these models must comply with. The question we pose is, can we use RNNs for fraud detection? As we know, RNNs are deep learning architectures with very interesting properties from the problem in hand. They are of cyclical nature, and this allows them to intrinsically embed the history of a card in their recurrent states. Moreover, they can deal with sequences of unlimited lengths. But can they beat the results of our best tree-based models? And can they be used in production given our strict engineering constraints? The model architecture developed is composed of three blocks. The first transforms the raw transactional data into an input feature vector the model can handle. The second is composed of gated recurrent units and is responsible for learning the representations of the cards by processing their respective sequences of transactions. Finally, the updated state for the card goes into the classifier block. It is concatenated to the input feature vector and then goes through multiple feed-forward layers to output the probability of the transaction being fraud. With this architecture and certain tweaks to the way we process events using GRUs, we were able to beat the baseline model on various metrics for two different real-life datasets, saving millions of euros in each. More details regarding our architecture and results can be found in the paper. In production, these models must function in streaming due to the strict throughput and latency constraints we have. This means our models must make predictions in no more than 200 milliseconds for the 99.999th percentile of the latency distribution, with a constant throughput rate of 500 transactions per second. The architecture of our system, depicted in this slide, must be able to pre-process the new transactions, fetch the GRU recurrent state for that card from a cache or embedded database, and feed the state as well as the pre-processed input into the GRU model to output a probability score for that transaction. Asynchronously, the new GRU state for the same card must then be updated on the respective entry of the database. Through numerous optimizations, mentioned in detail in our paper, we were able to output predictions with an average latency of 4 milliseconds and 127 milliseconds on the 99.999th percentile. Thank you. And please check out our paper where we enter into detail on how we deal with such big transactional datasets, on the domain-specific techniques we employ, on how we deal with scorable and non-scorable events while maximizing our GPU's usage, and on the various engineering optimizations which allowed our models to comply with our strict production constraints.